Welcome to the module titled Properties of Internal Energy. In this module, we will explore some fundamental characteristics of internal energy. We have seen that the first law of thermodynamics states that du, the infinitesimal change in internal energy, is equal to the infinitesimal change in heat, delta Q, plus the infinitesimal change in work done by the system, delta W. Now, what if there is no work being done on or by the system? If the volume remains constant, there is no compression or expansion work done on or by the system. As we neglect all other types of work for now, the work flow between the system and the surroundings is always zero. This naturally means that when the volume is constant, the change in internal energy is equal to the heat exchanged between the system and its surroundings. Indeed, when we, for instance, heat a system at a constant volume, all the heat is utilized to change the internal energy. We denote the heat exchanged between the system and its surroundings at a constant volume as QV. Note that this equation states that a change of a state function u is always equal to a change of a path function q. In general, heat is dependent on the precise path of the state change. But in this scenario, this change happens at a constant volume, which defines a specific path. This equation further means that the heat that a system exchanges with its surroundings at constant volume, whether it is added or removed, allows us to determine the change in internal energy since they are equal. Now we will introduce a new quantity, the derivative of the heat exchanged at constant volume with respect to temperature. This derivative is taken along the path of the constant volume. Along this path, the exchanged heat is equal to the change in internal energy. Hence, this quantity is equivalent to the partial derivative of internal energy with respect to temperature at constant volume. The condition of constant volume is important here because internal energy, U, depends on several variables and can be differentiated in different directions. This property is referred to as the heat capacity at constant volume, CV. Since internal energy is an extensive property, the heat capacity at constant volume is also an extensive property of a system that it characterizes. Naturally, we also introduce molar heat capacity at constant volume, which is an intensive property specific to a system or substance. To summarize, at constant volume, the dependence of internal energy on temperature is defined by the heat capacity at constant volume CV. Let us consider the total differential of internal energy. Mathematically, we can formally treat internal energy U as a function of two variables, T and V. Using the definition of the total differential, we obtain the following expression. The total differential of internal energy is the derivative of internal energy with respect to temperature at constant volume times dt plus the derivative of internal energy with respect to volume at constant temperature times dV. We have just deduced the first derivative, which is represented by CV. The term representing the change in internal energy with respect to volume at constant temperature is referred to as the internal pressure, often symbolized with pi T. Hence, the total differential of internal energy is CV times dt plus internal pressure times dV. Both these variables, heat capacity at constant volume and internal pressure, are temperature dependent and are specific to the system in question. When it comes to the dependence of internal energy on state variables, ideal gas represents a special case. In the model of an ideal gas, particles don't interact with each other due to the absence of intermolecular forces. Therefore, for an ideal gas, a change in volume alters neither the state nor the internal energy of its particles. Thus, the internal energy of an ideal gas is independent of volume. Its internal pressure is zero. The total differential of internal energy for ideal gas is always Cv times dt,